Most of the people around the globe would have heard of this mysterious object in the universe, which have puzzled us, continue to puzzle us, and will puzzle us in the future. This mysterious celestial body, which doesn't cure anything, was very famous even when it was just a mathematical equation back in 1950. Became a star by engulfing and forming from stars, and got a very famous name, which puzzled not only the scientific community but also common man. It was named the Black Hole. Black holes was named in the year 1967 by an American astronomer John Wheeler. Many of us think that black holes was first introduced to humankind when jumping out as one of the solutions to Einstein's field equation. But the idea of a body so massive that even light could not escape was briefly proposed by English astronomical pioneer and clergyman John Mitchell in a letter published in November 1784. Mitchell's simplistic calculations assumed that such a body might have the same density as the Sun and concluded that one will form when a star's diameter exceeds the Sun's by a factor of 500, and this surface escape velocity exceeds the usual speed of light. Mitchell referred to these bodies as dark stars. He correctly noted that such supermassive but non-radiating bodies might be detectable through the gravitational effects on nearby visible bodies. But first let us revise upon how black holes are formed. Alright, initially no one believed that there will be something like black holes out there. But as the scientific community started to accept their existence, the next question that popped out of their mind is how they are formed. Now, we do have a pretty sure idea on the formation of black holes, but still, scientists are wondering whether there are any prehistoric black holes, and if any, how would they have formed? Let's come to this topic in a minute after seeing how current black holes are formed. Black holes are formed at the final stage of supermassive stars, but luckily, our Sun does not qualify as a star to form a black hole, though they become a neutron star. We all know that for a star to sustain, it needs fuel, and for our stars, the fuel is hydrogen. There's a constant tug of war that's going on inside a star ever since its birth to its death. It's a war between nuclear fusion and gravity. We all know that gravity is the universal force of attraction and tends to bind matter together. Now, this nuclear fusion, on the other hand, releases energy by combining two atoms together. The energy released is enormous and fights against gravity in the opposite direction. As long as there is fuel, that is hydrogen in the star, the nuclear fusion will be tasting its temporary victory. But the moment the fuel empties off, everything fades within the star. Gravity starts to gain control and binds matter together, making the matter to move inward towards the star's core. This results in the shrinking of the star. As the mass of the star is compacted in a limited amount of space, the gravitational force exerted by the star increases enormously. As the gravitational force increases, the escape velocity increases as well. Now let us see about what is escape velocity. Escape velocity is the velocity needed by an object to overcome the gravitational force exerted on it by another object and escape from the other object's gravitational field. As the star continues to shrink, the escape velocity of the particular star becomes and exceeds the speed of light. As we all know that the velocity of light is the limiting velocity of our universe, no object travels faster than the speed of light. So the light that is emitted by the star is no longer seen by the outside universe, as the light never travels faster than its own speed. As a result, that particular star becomes invisible and officially becomes the black hole. Since our star has officially become a black hole, let's take a moment to take a glance on event horizon. Event horizon can be defined as a boundary beyond which no object can escape black hole's grasp. As you approach event horizon, the escape velocity slowly increases towards the velocity of light, and at the event horizon, the escape velocity is exactly the velocity of light. Beyond the event horizon, the escape velocity is beyond light's velocity, and this is the exact reason why black holes don't give anything out. Now, let us take look at an equation that we would probably have known since childhood. It's F is equal to m into a. Here, F denotes force, in our case is gravitational force, m denotes mass, and a denotes acceleration. Since from this equation we can conclude that as mass of an object decreases, the force exerted by it decreases. In our case, as mass of a black hole decreases, its gravitational force decreases, and as a result, its event horizon shrinks. On the contrary, if it engulfs any other celestial body, including another black hole, its mass increases, and as a result, its gravity increases, and so as the event horizon. This can be explained by Einstein's famous equation E is equal to mc squared. As the mass becomes negative, the compromise should be on the energy since the speed of light can't change. Now, we might wonder what will happen to the stars that don't follow a black hole, like our sun. It undergoes supernova explosion and becomes a white dwarf or a neutron star. We will cover up white dwarf and neutron stars in another video. Even the stars that form black holes undergo massive supernova explosions, which is nothing but an explosion that kills off the majority of the star while only the core remains. Scientists have been believing the black holes don't give up anything. Even great minds like Stephen Hawking was thinking like that until he figured out the impossible is possible. His mathematical calculations proved that black holes indeed emit radiations. Stephen Hawking was so disturbed by this result, he spent many days and weeks perhaps rechecking his equations and working out again and again in his mind. How many times he may work out the equation, the result was the same. So how does black holes emit radiation? If the escape velocity was greater than the speed of light, why do the black holes produce a special type of materials that travels faster than light? Well, the answer lies in quantum mechanics. Quantum mechanics states that there is no place such as void in this universe where there is no particle. Every space that we think is devoid of anything is constantly filled with particles. Let us take a random space that is empty, devoid of any particles. Now, due to the laws of quantum mechanics, a particle and a negative particle appears at its empty space, flies through it, finds one another, and finally gets destroyed. This happens at all spaces. Since this happens everywhere, it happens even near a black hole, even inside a black hole probably. These positive and negative particles are called pseudo particles or fake particles as they are not real particles, but they do have an impact and we know that they are there. Assume that the black hole sucks these negative particles and the positive particle escapes. Since this extra positive particle will not be destroyed by any other negative particle, it will become a real particle and comes out as radiation. From our observations, it will look like that the black hole is emitting the radiation, but the fact is, the radiation does not come from it but outside of it. Since the particle that went inside a black hole has a negative mass, it will decrease the mass of the black hole and as a result, the black hole shrinks. It shrinks continuously if it doesn't engulf any nearby matter and finally evaporates. There are various arguments about the end of the black hole, but we won't be seeing anything like this soon. Some scientists estimate that a black hole that have formed at the dawn of the universe will not evaporate even until the end of the universe. This radiation is famously called as Hawking radiation. Check out our short of the sequence video on black holes below and subscribe to our channel and our blog for more great contents.